question is going to be on motion. And we're going to start out talking about position. Position is where an object is relative to some origin that we've decided on. The symbol for it is going to be x, and it's going to be in meters. So here's an example. We got Mr. Lynch and Mike and Sarah standing along a number line. It's marked off in meters. What's Mr. Lynch's position? Actually, that's a trick question. You can't really tell. Because we didn't tell you where to measure from. Now, if I ask it this way, it makes a little more sense. Where are the positions of each of them relative to Mr. Lynch? So if I look on here, Mike is 1, 2, 3, 4 meters east. So Mike is 4 meters east. And Sarah would be 6 meters. What are the positions of each relative to Mike? Okay, look like that. Mr. Lynch is 1, 2, 3, 4 meters away to the left, or 4 meters west. Or we could write that as minus 4 meters, and then actually relative to Mike, his position is 0. He's at the origin. And Sarah is at 2 meters east. Or another way to say it would be plus 2 meters. Position's a vector, so we must include direction. Now, magnitude is just size of, so the magnitude of Mr. Lynch's position relative to Mike. I don't have to worry about the direction for that, so it would just be 4 meters. Now, displacement. Displacement is defined as the change in position. So it's delta x. And I can find it by doing final minus the initial. So we got this person going 3 miles east, so it starts here someplace. There's 3 miles this way. Turns around and goes 8 miles that way. Alright. Now, here is the displacement. So it's changed from where he started, so he ended up 5 miles west. Or minus 5 from where he started. Our distance is just how far total. Okay, it's a scalar. There is no direction involved. So what is the distance they traveled? He went 3 miles east and 8 miles west. He just went 3 miles and 8 miles for a total of 11 miles. Now, speed and velocity, in the English language we use those interchangeably, but they actually have a slightly different meaning. Speed is how fast something is moving. Okay, and it's a scalar. All right, and then velocity is how fast with direction. So it's a vector. Like I said, we use these kind of interchangeably. If I'm driving down the street in my car and I'm going 50 miles an hour north, My speed is 50 miles an hour, my velocity is 50 miles an hour north. So it's easy to see why I use them interchangeably because the amount is the same. But we really should always have direction when we're finding velocity. So finding constant or average speed problems, we'll use the equation V, put a little line over it, meaning average or constant speed. It's going to equal delta x over delta t, change in position over time. Now be careful when using this equation. It only tells you speed. It only tells you your average speed. So let's say that I was driving in my car, I went 50 miles in 2 hours. That would mean my average speed would be 50 divided by 2, 25 miles an hour. But it doesn't tell you anything about any of the specific speeds anywhere along the trip. I stopped, I started, I sped up, I slowed down. All I know is the average for that. Or you can use it if it's a constant speed problem. Because it's constant speed, the speed didn't change. It'll work for that too. But those are very rare. Now, v is the average velocity if you use displacement for x. It's the average speed if you use distance for x. So if I do this equation, this is going to be speed if this is distance. Okay. If I use the same equation, but I use displacement here, then I'm going to get velocity here instead of speed. A couple examples of that on the next page. Okay. A car travels 200 miles north in 5 hours, stops for a half hour, then south for 300 miles in 6 hours. So if I was to sketch it, it would look like this. 200 this way, turn around, and go 300 this way. Okay, now, part A, we want the distance. I'm going to use the letter delta x for distance, but I have to remember that it's not a vector in this case. I went 200 one way, then 300 the other way. Altogether, I went 500. For B, the displacement, is the change in position. So it went 200 miles north, then turn around and went 300 miles south. This displacement is just going to be 100 miles south. Part C, average speed. For average speed, I want to use distance over time, not displacement. So it's going to be 500 miles over. Now, for the entire trip, it took 5 hours, and then half hour, and then 6 hours, so that's 11 and a half. And that's going to give me a value of roughly 43.5 miles per hour. Now, if I want to find the average velocity, I'm going to use the same equation. I'm going to use displacement. So the displacement was 100 miles south. Divide that by the 11.5 hours of time, and I will get 8.7 miles per hour. So, okay, our last little example here. This time I'm giving you the velocity. And I'm going to write down my givens over here. I have the velocity is 30 meters per second west. Okay, I have time is given is 6 seconds. Now I'm looking for how far. I'm looking for displacement. Okay, so for part A, I use this equation, and I rearrange it to get the displacement by itself. Get delta x is delta t. So now I can plug in. I'll get 30 meters per second. And then I'm going to multiply that by the time of 6 seconds. It's going to give me 180. The seconds are going to cancel, and I'm left with meters, which makes sense because it is distance. Now, since I said how far here, it sounds like I'm not looking for direction, so I'm not going to worry about east or west. Part B, write the equation for its displacement as a function of time. So again, if I start from here, okay, delta x, v bar delta t, okay? Now his displacement, delta x, wait, this is a vector, so I have to be careful. Since its velocity is 30 meters per second west, let's say make that negative, and then times my time. So now I could plug in any time and find out how far I went. Now, for part C, okay, it starts 60 meters west of the observer, and I want to know its position relative to the observer as a function of time. So if I take a look at this, I might do something like this. I have the observer here. Okay, and then I have the car starting out here, going this way with a velocity of 30, but he's already starting 60 away to the west. So I have to take that into account. Okay, now I know that this is going to give me his displacement. All right, so at time t equals 0, okay, he won't have gone anywhere. He's going to be at minus 60. Okay, but then time t equals 1 second, he'll have minus 30. He'll be 30 more to the left, so he'd be at a position of negative 90, and so on. So if I was to make up an equation for that, it would look something like this: minus 30t minus 60.